Yeah? Okay. Kirchhoff. What nationality do you think he is from his name?
Russian.
Yeah, Russian. Russian, yeah. Physics, electricity, and we just done Kirchhoff, so we only have actually 3 more topics left. Work and power. So we're going to do 2 today, work and power and this one, and then on Friday we'll do 1, and then the rest will be for the essay. Okay, so work and power now. So of course you already know a bit about work and power because we did it in mechanics. Work is force times distance. But it's different, of course, for electricity. It's not the same formula.
Force multiplied.
Correct. Yeah.
Q into D, I think.
That's almost it. That's for power, actually. Yeah. Right. It's just opening now. By the way, please stop saying into for multiply and by for divide. In Ireland, it's the other way. So in Ireland, when you say into, it means divide. And when you say by, it means multiply. Only in the UK do they say it this way. Everywhere else is the opposite. You see, you didn't know that, did you? No. So, yeah, but that's maybe British influence in the English. Exactly, yeah. So you will totally confuse people in Ireland, because I'm a maths teacher. I know when you say it, you mean it the other way, but nobody else will know that. Yeah. So just keep that in mind when you're saying it. I think it's safer. It's safer because it's universal. Yeah. Right. Work and power. If you can write this down. Yeah, like in America and in Ireland and other places, they'll say into to mean divide.
And when it's fraction like 3 upon 5, the way I say it, it's also wrong.
It's also wrong. Yeah.
3.
I think we don't use upon here, but people, if they were to guess, they would not say divide; they would say multiply.
No, like 3 over 2. Oh,
yeah, you would have to say over here. Yeah. 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 Now the only reason I'm saying this, Mir, is because the more common usage would be opposite of what you're saying. So you have some bad habits from Cambridge English, unfortunately. Yeah, it's good to know this. Okay, so what we're going to have a look at first. So we care about electricity because of its ability to do work. When you think about everything in your life, laptop, heater, TV, iPhone, how does it get its life? Yeah, it gets all of its ability to do work from electricity. So it's a very important topic. So everything in your life, really, its energy is being converted from electricity. So it's a very important topic. So that is, electricity is a form of energy, which you know. And remember what we said 1 volt means. 1 volt means 1 coulomb of charge can do 1 joule of work. So using that definition for volt, we can get this simple formula. That the work done is equal to the charge multiplied by the volt. But also remember we have another formula for Q. We can say IV. So we can also have this formula. But also we can divide by time. So if I put the T under here, remember work divided by time is power. So we can get this formula you said earlier, Mishri, for power. Power is IV. And if we think about our triangle, you remember IV or? What's another formula for V in our triangle? IV or. Hang on, what am I doing?
No.
I'm replacing the V, yeah.
So it's I square
V is I.
I can't do this in my head because I'm hungry. IV or. What do I want to replace?
The V is.
Do I have a mistake here?
No.
I think I do.
No.
No, VIR.
Oh my goodness! Well,
Yeah,
sorry.
V the top.
Sorry. VIR, thank you. So V equals IR. So if I replace the V here, I get I squared or. That's another formula. Or I could replace the I. So if I replace the I with V over R, so if I replace the I here, I get V squared over R. Now, I don't expect you to remember all of these, okay? What I really expect you to remember, I want to show you that you can make whatever you need for the question. So the two key ones to remember, I think, is the triangle, as normal, the formula for power, which is IV, but remember you can replace these with the triangle. And then the last one, the first one, the work, W equals QV. So these are the three ideas I want you to remember. Okay, so if you can just, let's make that a little bit neater. So number one, you should remember your triangle. Number two, that Q equals, W equals QV. And number three is P equals IV. And number one, you can put it into the two or three to make new formulas.
In the exam, they will bring this three formula.
These three, well, no. These two are in the formula book, but this I don't think is. Yeah. Continue?
Yeah.
Okay. So, when a current is running through a resistor, initially there's been no charge passed through it until at some point there is a charge. All the time the voltage stays constant. Let me draw the graph. If we picture here, look, here's a resistor, and here is a current, and here is our ammeter, and I want to make a graph here. And what do I want to put on the x-axis? Initially there is no charge passed through until some point there is a charge. All the time the voltage stays constant. So I think I want to put a V and a Q here. Yes. Okay, so this is a little bit tricky. I'm going to put a voltmeter here. So the voltage doesn't change. And does the current change? No, it's going to be constant current, constant voltage. Like, for example, maybe, let's just say I. Maybe this will say 3 amps and this will say something like 2 volts, and it will stay constant. But I want you to imagine the charge. So the charge is coming along here. So at the very beginning, is there any charge that passed through? No, we're waiting for the charge. And then what will happen? The charge will pass through. So imagine I can count the charge that passes through. So imagine these are 1 coulombs. Yeah? So at the very beginning there's no coulombs. And then after some time, after 1 second, how many coulombs pass through? 3. And then after 2 seconds, 3 more. And another second, 3 more.
You mean that it's adding?
Yeah. Because remember, 3 amps is the same as 3 coulombs per second. Do you remember that? So each second I get more and more coulombs of charge. So as the Q increases, I get, as time goes by, I get more coulombs. But the voltage doesn't change, does it? It still stays at 2 volts. So if I was to plot the charge against the voltage, what will the graph look like? What do you think? No, because that would mean the voltage is increasing as the charge increases. A straight line. And here this would be 2. Now, if you calculate the area on this graph, what's the unit? Well, the base is in units of coulomb, and the height is in units of voltage. Yeah? So if you have a Q multiplied by V, the area, what does that represent? Well, if you go back to my notes here, I think I wrote it on the last slide.
What?
Yeah, when you have Q multiplied by V, you get the work. So what I'm trying to say is that if you plot voltage against the current, not the current, the charge, the area on the graph here is the work here. Basically, if you have a QV graph, the area is work. That's what I'm trying to say, and I'm trying to explain it with this example. You don't need this example. If you're happy with just accepting this fact, fine. So if you can draw this as an example here. So can you see that when more time passes, we have more charge? And if we have more charge, then more work has been done. You got this?
Yeah.
Continue? Right. So notice how the area equals work. Now what happens if we have a capacitor? So this is more interesting, much more interesting. So we have a capacitor, we have our, measure our current, and we measure our voltage, and we want to know what does the graph look like when I have V here and Q here. Now, what happens when the charge comes along? Well, it builds up in the capacitor, doesn't it?
Yeah.
And you remember the graph for it? It decreases. Now, okay, at the very beginning, the graph actually looks like this. First it charges up, and then when you remove the power and let it discharge, then it discharges like this. This is what we were doing in class. Anyways, that's not really too important. What is important is the formulas. Do you remember the formula for Q? It's Q0 E minus, come on, T
Upon tau. Divided by tau.
Thank you. And then here V equals V0 E minus T over tau. Yes. We have these from last week.
Yeah.
Now watch what happens if I divide these. Q divided by V equals what?
Q naught
Q0 over V0. Yeah. So now we can say V equals V0 over Q0 multiply Q. So this is like, if this is V and this is Q, this is like Y equals M times X. So what type of graph is this?
slope.
A straight line with a slope. And where does it pass here? Through the origin, because there's no C. So there's no C. So the graph looks like this for the capacitor. And this is important because if I want to know what the work is, what would it be? Work is a half QV. And this is the formula for the work if it's a capacitor. Now compare that to what you did earlier. What formula did you have earlier? Work equals QV. That's if it's a resistor. But if it's a capacitor, it's this one, it's half of it. So That's a very common mistake students forget in the exam, that it's a different formula for capacitor. Please make careful note of this. Okay, we're good?
Yes.
Now, do you remember from capacitor, we have a formula for Q. Does anyone remember?
COD. COD.
CV.
Thank you. CV.
Okay.
Yeah, that one. So if I put that in here, we can make this formula, which is very common. The work a capacitor can do is a half CV squared. This is the work a capacitor can do. We can use both. Can do when charged.
Why V0 over Q0 equal M?
No, I'm just making a comparison that it's like the formula y equals mx, that you have variable, constant, and variable. Do you know what I mean? You know what I mean by comparison, do you? Yeah, compare two things, yeah. Okay? Continue? Continue? Yeah, okay. So these are our two formulas we have. Yeah, you have these? These are for capacitors. Capacitors. Oh, come on, what's happened? Ah. Right, let's try this one. If you can write this down and we'll do it. I mean, you can try to do it if you want, and I'll do it in a minute. I don't think it's too hard. We just use the formulas from today. Do you want to try this? Fawn, do you know what this is? Do you know it? Very good. Yeah. So, first current, then resistor, then charge, then work.
What is for which power?
Yeah, remember what a watt is?
Yeah,
It's 1 joule per second.
For power.
It's for power, yeah. We have answers? Yes? Can we do this now? No.
I want to see for the C.
The C?
How much charges pass through the overall?
C?
I know Q.
Q?
I'm talking about part C.
Oh.
Do we say that that's one, 10 or 10?
Why you guys are like?
10,000.
Yeah, sorry.
You thought the same thing I thought,
Yeah, I
yeah.
did.
Yeah. Right. So the power, let's do this now, is 10,000 watts. And the voltage?
220.
220 volts. What did I want first? The I, was it? Yeah, so we can just say P equals IV. So I equals P over V, which is 10,000 over 220, which is 45.45 amps. What was part B now? What did I want? Yeah, so the OR equals V over I, which is 220 over 45.45. What is it? 4.8 ohms, yeah? Okay. C,
Charge in 1 hour.
so remember Q equals IT. That'll be 3,600 times 45.45. What's that now? Nobody remembered that, huh?
Wait now.
16362.
Yeah. 164 kilocoulombs. And D, what's the last one that I want?
Work in 1 hour.
And work, there's two ways to do it. Well, do we have we have Q and V, don't we?
Yeah.
Yes.
So this is 36 megajoules.
So,
Yeah?
the Q is already in 1 hour. So we just put the value of Q and we.
Mhm.
For example, in the exam, the part C is not there. And it says just find the work in 1 hour.
Yeah, now there's another way you can find the work, because you have power is work over time. So you could have done work equals power multiply time, which is 10,000 times 3,600, and you get the same answer, 36 megajoules. Yeah? Can I go to the next one? Yeah, there's just one more example. So try this one, and then I'll do it as well. So this one now is a capacitor. Wrong. What's MF?
Micro mini
Millifarads. Millifarads. Yeah, okay. Try this one. Of course, part B should say how much energy is stored, not how energy is stored in the capacitor. Yeah. I can hear Arabic behind me.
Do we take the one?
Yeah, yeah.
Oh yes, yes. Oh come on, Mir, you know what milli is. 10 to the
Minus
3.
3 minus 3.
Yeah. It's confusing me. Minus 6.
I said 3.
Yeah, believe him.
Okay, alright.
Which part? B. I gave you the formula today. Q equals a half. Oh, sorry. Work equals a half CV.
Square.
No, that's
QE,
something else.
QE.
Sorry, oh my goodness, sorry. It was this one from, it's gone. Right, here. A half QV for a capacitor. Or a half CV squared. You can use both. Yeah? Energy and work, the same thing here. Yeah.
Energy is work.
In this way it is, yeah. Whoops, that's not it. Two more minutes and then I'm going to do it. Sharif, what are you doing? Are you like talking to Siri or something? What's going on over there?
My phone.
Oh, that's your phone. Alright. Siri, what is the answer? Right, can we do this one now? Iyad, which part are you on?
3.
3.
C.
C, yeah. Right, let's have a look at it. Okay. What's the voltage here? 120 volts. And the capacitance? Yeah, 100 millifarads. And what do I ask you for first? The charge. So you have Q equals CV equals 100 times 10 to the minus 3 times 120, which is 12? 12 coulombs. Is that right? Right, what do I ask you for B? The work. The energy. The work. It's a half QV or a half CV squared. Yeah. So a half QV. So that's 720 joules. Or you could say it's a half CV squared, which is a half times 0.1 times 120 squared, which I assume is also 720. Yeah. What do I want in C? Time to discharge. Now, do you remember the formula for the time to discharge?
5 now.
Yeah, 5 tau. And what's tau? The formula for tau. Oh.
I have done in
Anyone remember tau?
Oh. Yeah.
Yes. Now, do we know the or?
We can't get it.
No.
We don't. Yeah, we can get it. We don't know it right now, do we?
No, we know it.
Do we know the or? Oh, I give it in the question, don't I? Yeah. So that's 5 times 100 times 0.1. So 50? 50 seconds.
Yeah.
I just need to understand.
Why is the R in the question?
Huh?
Where is the R in the question?
And lastly, guys, look up. What's happening here is the capacitor is discharging through a light, and the light is giving off work, it's doing work. So my last question is, what's the power? So what's the formula for power? IV. But here I think it'd be better to use work over time, because we know the work, we have that earlier, it's 720 joules over 50. Yeah, so roughly
14.4.
about 14.4 watts. Good.
Yes,
Good.
Yep.
very good.
Why you have to write?
Yeah, why this? No, Fuan, what's this called?
Nearly.
Nearly, yeah, good, yeah, no, right, yeah, nearly, yeah, roughly, or approximately, You know this word? So, the reason, does anybody know why did I write this here?
Why?
Yeah, why, I'm asking.
Because
It's because of this part. Remember I said, it's not really 5, because on the graph it never actually gets to 0, so we just say that this is roughly 5 time constants. Okay, so we're okay with that now, yeah? Go on.
But if we use IV,
We get a different answer.
I don't know.
I don't know. Well, let's see what happens. Do we know the I? No. Do we know the V?
Yes.
Yeah, what is it? 120. Now, how can I get the I if I use VIR?
I equals to Q1T.
I equals V over R.
Yeah, 150
Yeah.
over 100.
So you can say P equals IV, but I is equal to V over R. So another formula is V squared over R. What's the V? 120. And the R? 100. So 120 squared, we get 144.
Yeah.
Now this is totally different, isn't it?
Yes.
Did I do that right?
I think
1.44.
the R in question B
14.4.
is different.
Oh, sorry, yeah.
D.
Yes, it is.
It's only equal
What's
to
different?
C. The R
Yeah,
only equal
yeah,
to
yeah,
C.
yeah.
Oh.
yeah. How to explain? Just give me 1 second and some coffee. I want to get this explanation right. I tell you now. The problem is basically this. This formula is actually for a resistor. But what's happening at the very end, when this is discharging, when you think about the graph, here's time and here's voltage, the graph is decreasing. And here's time and here's current. What's happening? It's decreasing. So if I was using this formula, P equals IV, this is if the I is constant and the V is constant. But are they constant? No. They're decreasing. They're decreasing. So what you could do is you could say P is roughly the average I multiplied by the average V. The V starts at 120 and then decreases to about 0. So what would be a average value to use, roughly? About 60. About. And what about the I? What does the I start with? Well, let's calculate it. VIR, I equals V over R. V is 120 at the start, and the R at the start is 100. So this is 1.2, so the average value could be 0.6, so this will be roughly 60 times 0.6, which is 36. Now this is still bad, because my answer is 14. Now the reason it's so bad is because the average isn't really 60. In fact, the average is less than 60, and the reason is, if the graph was going like this, the average would be 60. But because the graph is dropping really quickly, the average is more like 30. And the average is more like 0.3 because it's dropping so quickly. So if you were to use 30 and 0.3, the answer is closer. But doing it this way is not great, and the problem is because the I and the V are decreasing. But doing it this way is more accurate because we know the total energy is 720. This is exactly right. And we know the time is, okay, it's not exactly this, but it's good enough, it's this. So this formula is the best one to use, it's most accurate. This one here is no good because the I and the V keep changing.
But why you use the answer question B to do the question B?
Yeah, because what's happening is the energy is coming from this. So the energy here will go into this. And the time here will equal the time here. So for example, if this is 50 seconds, look up. If this is 50 seconds, how long will this light be on for? 50 seconds. Because when this is gone, no energy left. So the time here will be the time this light is on for. So the power of the light, the time will be 50. And the energy here is the energy here because it gets its energy from the capacitor. So the energy here will be 720. If we try to use I and V, it's a problem because the I and the V, they keep changing. It gets smaller, smaller, smaller. So the formula doesn't work. Are we okay with this now?
Yeah.
Go on.
Sir,
Go on, it's okay? Yeah.
for power itself, but use what converting?
For capacity.
Yeah, for capacitors, yes, because the problem with capacitors is the I and the V keep changing. Yep. Okay. Right, what I'll do is I'll let you work on these for 5 minutes and then we'll start the next lesson. Can I close the other one?